Hey again. In this video, we're going to go over why the alternating series test for convergence makes sense. It's very cool. It has to do with basically looking at a number line, right? And that's what we're going to do. We're going to make this very, very simple. We're going to look at a very cool series, and let's expand it out. We actually took a look at this one in video 1, and we proved that it does converge, so we're going to look at why it makes sense. So -1 to the n times 1/2 to the n. Well, when we expand that out, we plug in 0. We're going to get our first term as 1. And then when we plug in 1, we'll get a negative, so it's minus 1/2 to the 1 is 1/2. And then plus, we'll alternate back to 1/4 when we plug in 2, 1/2 squared. And then minus 1/8, and then plus 1/16, and so on and so forth, until we get to that nth term, -1 to the n times 1/2 to the n. Very nice. Okay, now from here, I'm going to draw vectors. And if you've never heard of what a vector is before, they're basically arrows, right? They give you an idea of the size and direction in which something is moving. And so those vectors, those arrows, are going to represent each of the term sizes as well as the partial sums as we go on. What do I mean by that? Well, if you take a look here, I'm going to start with this point here. And I'm just going to draw out vectors. So I'm going to draw out a line all the way out to here. That would represent the size of 1. We've added 1. When we subtract 1/2, we're going to roughly go to about halfway in between, right? So this thing right here is your minus 1/2, and this is your plus 1. Now we end up here at about 1/2. Then we're going to add 1/4. So 1/4 would be about half of that to about here. That's where we add 1/4. And then minus 1/8 is going to be here, about half of 1/4. And then add 1/16. Oh, yeah. And then we keep on going on and on and on. What you see here are the conditions at work. And what we talked about is, in order for the alternating series to converge, the terms represented by the lengths of these arrows and their directions, depending on if they're positive or negative, those terms need to decrease in size, or in absolute value, to 0. And that would mean convergence. Well, here we go. If they decrease in size, what that means is we'll end up fitting nicely somewhere between 0 and 1. We end up converging as long as they go to 0, because if they don't go to 0, here's what happens. Let's say, just for giggles, that we locked up at 1/16, and then we just kept alternating at 1/16. Now we stop decreasing in size, right? That would be a diverging series, because the nth term test would show that we didn't go to 0. So you've got to not only decrease in size, but go to 0. If you don't, even though you end up like kind of oscillating or changing, values again and again and again, you never quite sit on one convergent finite value. So that's why we've got to go to 0. So that doesn't happen. And you got to keep decreasing so you can get to 0. So if these things keep decreasing on and on and on, like so, eventually the vectors, the size of these terms, get so tiny that we go to 0, so that even though we're alternating values, we just start adding 0 at the end of things, and we'll eventually converge. So that's it. So you've got to have terms that decrease in absolute value and go to 0. Otherwise, we'd have to show that this thing diverges by a different test. Isn't that cool? So that shows you why the alternating series test for convergence works. I will see you in the next video, where we're going to be going over error and why error works. It actually has a lot to do with this image. But I wanted to get this one down first in a short yet sweet video. See you next time. Peace.